280 light years away, there's a planet that, according to every model astronomers had built over the last 2 decades, simply should not have an atmosphere. It orbits so close to its star that a single year lasts just 10.5 hours. Its dayside sits permanently locked toward a sun so intense that its surface should be a bare, blistering ball of exposed rock and molten lava, stripped of every trace of gas billions of years ago. And yet, when the James Webb Space Telescope finally measured it directly, the numbers came back wrong in a way that immediately caught the attention of the entire planetary science community. Not wrong in the sense of a measurement error, wrong in the sense that the planet was measurably, unmistakably cooler than physics said it had any right to be, if it truly were the bare, airless rock everyone assumed it was. This is the story of TOI 561b, a world astronomers are now openly calling impossible, and exactly what Webb found that's forcing scientists to rewrite what they thought they understood about how planets survive. And let's start with why this planet was already considered strange long before Webb ever pointed toward it. TOI 561b sits roughly 280 light years from Earth in the constellation Sextans, orbiting a star that is genuinely ancient by galactic standards, nearly twice the age of our own sun. That star belongs to a region of our galaxy astronomers call the thick disk, a population of some of the oldest stars in the Milky Way, formed at a time when the raw ingredients available for building planets were dramatically different and noticeably poorer in heavier elements like iron than the material our own solar system eventually formed from. TOI 561b itself has roughly twice the mass of Earth and a radius about 1.5 times as large, technically classifying it as what astronomers call a super-Earth, a rocky world larger than our own planet, but still fundamentally built from solid material rather than the thick gas envelopes surrounding worlds like Jupiter or Neptune. None of that alone would be particularly shocking. What made TOI 561b stand out from the very beginning was its orbit. TOI 561b belongs to an extreme rare category of exoplanet astronomers called ultra-short period planets, worlds that complete an entire orbit around their star in less than 11 hours. TOI 561b's own orbit clocks in at just 10 hours and 34 minutes, meaning its distance from its host star is roughly 1/40th. The distance separating Mercury from our own sun, an almost unimaginably tight orbit that leaves the planet permanently tidally locked, one side forever frozen in blazing daylight, the other locked in permanent darkness, exactly the way our own moon always shows Earth the same face. At that kind of distance, even orbiting a star slightly smaller and cooler than our sun, the physics involved is brutal. Any planet locked that close to its star for billions of years should have had every trace of its original atmosphere stripped away long ago, blasted off into space by relentless stellar radiation, leaving nothing behind but scorched, bare rock. That's not speculation. It's one of the most well-established, consistently observed patterns in planetary science, confirmed across dozens of previously studied ultra-short period planets. TOI 561b was supposed to follow the exact same pattern. To really appreciate why this particular result caused such a stir, it helps to understand just how consistently the opposite outcome has played out across every previously studied ultra-short period planet. Astronomers have cataloged a number of similarly extreme rocky worlds over the past decade, planets like 55 Cancri E and Coro T7b, close orbiting rocky bodies that, when directly measured, consistently show dayside temperatures matching or exceeding what a bare, airless rock prediction demands, with little to no evidence of any meaningful heat redistribution. That consistent pattern is exactly why the field settled so firmly on the assumption that ultra-short period planets simply cannot retain an atmosphere, a conclusion drawn not from a single case, but from repeated, independently confirmed measurements across multiple different star systems. TOI 561b is the clear outlier in that entire dataset, the first planet in this extreme category to show a temperature signature that so strongly and so specifically points toward genuine heat redistribution rather than simple, direct, unshielded stellar bombardment. An international team of astronomers, led by Carnegie Science researcher Johanna Teske, set out to directly test that assumption using an instrument aboard James Webb Space Telescope called NIRSpec, short for the Near-Infrared Spectrograph. The technique itself is elegant in its simplicity. As TOI 561b swings behind its star during each orbit in what astronomers call a secondary eclipse, the combined light from the star and planet briefly dims by exactly the amount of light the planet itself was contributing before disappearing from view. By precisely measuring that dip, researchers can calculate the actual thermal emission, and therefore the actual surface temperature, coming directly off the planet's permanently sunlit dayside, without needing to physically visit the planet or capture a literal image of it. If TOI 561b really were the bare, airless rock every existing model predicted, its dayside should have registered a scorching temperature near 4,900 degrees Fahrenheit, roughly 2,700 degrees Celsius, hot enough to vaporize most metals, consistent with a planet baking directly under intense, unfiltered stellar radiation, with absolutely nothing shielding or redistributing that heat. When Webb's data finally came back, the measured temperature was 3,200 degrees Fahrenheit, right around 1,800 degrees Celsius. Still extraordinarily hot by any ordinary standard. Hot enough to keep the surface in a permanent molten state, but nearly 900 degrees Fahrenheit cooler than the bare rock prediction demanded, a temperature gap far too large to explain away as simple measurement noise or minor uncertainty in the models. That 900-degree discrepancy is the entire heart of this discovery, and it's worth understanding exactly why researchers immediately zeroed in on it as such a significant result. In basic planetary physics, a bare rocky surface with no atmosphere has almost no ability to redistribute heat. Whatever radiation hits the dayside simply bakes that exact spot, since there's no surrounding gas available to carry warmth around to other parts of the planet. A significantly cooler than predicted dayside temperature, especially one measured this precisely using an instrument as sensitive as Webb's NIR spec, strongly points toward exactly one thing. Something is transporting heat away from that scorching hot spot and spreading it elsewhere across the planet. And the only physical mechanism capable of doing that at this scale is an atmosphere, a layer of gas thick enough to actually carry and redistribute thermal energy, the way our own Earth's atmosphere constantly does. Researchers on the team didn't jump straight to that conclusion. Responsible science means ruling out every plausible alternative first, and the team spent considerable effort doing exactly that, treating the atmosphere hypothesis as the last explanation standing rather than the first one reached for. Could the molten surface itself, an ocean of liquid rock believed to cover much of TOI 561b's dayside, be responsible for spreading heat around on its own without needing an atmosphere at all? The team concluded that while a magma ocean could shift some heat around locally without an atmosphere actively trapping and circulating that warmth, the permanently dark night side of the planet would almost certainly remain solid rock, limiting just how much heat transfer a molten ocean alone could realistically account for. Could a thin layer of vaporized rock, essentially a wisp of mineral gas boiled directly off the superheated surface, explain the temperature gap instead? The team tested that possibility too, and found it similarly couldn't account for enough cooling on its own to fully explain what Webb had actually measured. One by one, the simpler atmosphere-free explanations kept falling short, leaving the team with an increasingly confident conclusion. TOI 561b appears to be wrapped in a genuine heat-redistributing atmosphere, sitting directly above its churning ocean of molten rock. Here's where the discovery becomes genuinely significant, well beyond simply confirming one unusual planet's temperature reading. If TOI 561b truly does possess an atmosphere, it directly challenges one of the most consistently observed rules in the entire field of exoplanet science. The idea that small, rocky planets locked into extremely tight, blisteringly hot orbits simply cannot hold on to gas over long cosmic timescales. TOI 561b isn't a young planet caught mid-transition, still in the process of losing whatever atmosphere it originally formed with. It's ancient, orbiting a star nearly twice the age of our own sun, meaning this planet has spent billions of years locked in this exact punishing orbit, continuously bombarded by intense stellar radiation the entire time. According to every existing model, that kind of sustained exposure should have completely stripped away any original atmosphere within a small fraction of that time span. And yet, somehow, TOI 561b appears to still have one. Researchers studying the data have proposed a compelling, if still somewhat speculative, explanation for how this could actually work. Rather than holding onto a fixed, unchanging atmosphere left over from its original formation, TOI 561b may instead be continuously generating and regenerating its atmosphere in real time, fed directly by its own molten surface. The team has described this possibility using the phrase wet lava world, imagining a planet where the underlying magma ocean is genuinely rich in volatile materials, elements, and compounds capable of vaporizing under extreme heat and rising up off the molten surface to form a thin, constantly replenished atmosphere above it. Under this model, even as intense stellar radiation continuously strips gas away from the top of that atmosphere and blasts it into space, the churning magma ocean below keeps bubbling up fresh material to replace exactly what's being lost, creating a kind of continuous equilibrium, a planet perpetually losing its atmosphere and perpetually regenerating it at roughly the same time, locked in balance for billions of years. Johanna Teske, the study's lead author, has been refreshingly candid about how much this discovery actually complicates, rather than simplifies the picture. In her own words, what makes this new data set so exciting is that it opens up considerably more questions than it actually answers. And that's genuinely the honest state of the science right now. Nobody on the research team is claiming to have definitively solved the mystery of TOI 561b. What they've established, using some of the most sensitive thermal measurements ever taken of a rocky exoplanet's dayside, is that the planet's temperature doesn't match the bare rock prediction, and that the most physically plausible explanation for that mismatch involves some form of active atmosphere. Exactly what that atmosphere is made of, exactly how it's being continuously regenerated, and exactly how a planet this small and this exposed has managed to sustain the process for billions of years, all remain open, actively debated questions that will require considerably more observation time to fully resolve. There's also something worth appreciating about the specific chemical history that makes TOI 561b's host star, and by extension the planet itself, so unusual to begin with. There's also something worth appreciating about the specific chemical history that makes TOI 561b's host star, and by extension the planet itself, so unusual to begin with, a detail that has become increasingly relevant as researchers try to piece together how a planet like this could have formed in the first place. Astronomers estimate the TOI 561 system formed roughly 10 to 11 billion years ago, placing it among the oldest known planetary systems with a rocky planet ever directly characterized. Old enough that it predates the formation of our own solar system by several billion years. At that early point in the galaxy's history, the interstellar clouds of gas and dust that eventually collapsed to form new stars and planets simply hadn't yet been enriched with anywhere near the quantity of heavy elements, iron, silicon, and other rock-forming material that later generations of stars, including our own sun, would eventually inherit. That means any rocky planet forming around a star this old, TOI 561b included, would have assembled itself from a fundamentally different starting recipe than Earth or any other rocky world in our own solar system ever had access to, potentially explaining part of why this particular planet behaves so differently from every model built primarily around planets that formed billions of years later under much richer chemical conditions. Because this star belongs to the galaxy's ancient thick disk population, it formed from material significantly poorer in heavier elements than the gas cloud that eventually produced our own sun and solar system. Planets forming from that kind of iron-poor, chemically primitive material would be expected to end up with a noticeably different internal composition and structure than planets like Earth, built from a chemically richer environment billions of years later. Teskey and her colleagues have pointed out that TOI 561b, given its age and the unusual chemical environment it formed within, almost certainly assembled itself under conditions genuinely different from anything present anywhere in our own solar system's early history, meaning this single planet may be offering researchers a rare, direct window into how rocky worlds form and evolve in an entirely different chemical era of the galaxy's history, one that predates our own solar system by billions of years. Think about what it actually means for a discovery like this to genuinely reshape scientific understanding, rather than simply adding one more entry to an already long catalog of confirmed exoplanets, a catalog that, as of 2026, has grown to include well over 6,000 confirmed worlds beyond our own solar system. For years, the working assumption across the field of exoplanet science has been relatively straightforward. Small, rocky planets orbiting extremely close to their stars lose their atmospheres permanently, and that process is essentially a one-way, irreversible street. That assumption has directly shaped how astronomers evaluate which planets are worth prioritizing for further study, how mission planners decide where to point increasingly limited and valuable telescope time, and how researchers model the long-term evolution of rocky worlds across the galaxy more broadly. If TOI 561b really is actively regenerating its own atmosphere from a churning magma ocean below, that assumption doesn't just need a minor footnote or exception carved out for one unusual planet. It potentially opens up an entirely new category of planetary behavior that current models simply weren't built to account for. A feedback loop between a molten interior and a thin, constantly cycling atmosphere that could, in principle, apply to other extreme, close-orbiting rocky worlds astronomers have already cataloged but never closely examined with this specific question in mind. It's worth being clear about the boundaries of what's actually been confirmed here, because the honest version of this story remains genuinely compelling without needing any exaggeration. Nobody involved in this research is suggesting TOI 561b could support life of any kind. Its dayside remains hot enough to keep rock in a permanently molten state, an environment about as hostile to anything resembling biology as any confirmed exoplanet in the current catalog. This isn't a habitability story, it's a planetary physics story, a genuinely surprising data point that challenges long-held assumptions about which planets can and cannot sustain an atmosphere, and under what specific conditions that atmosphere might actually be able to persist, or even regenerate itself, across billions of years of continuous punishment from its host star. Consider, too, just how demanding a measurement this actually was for Webb's instruments to pull off successfully. 2I561b is a relatively small, faint target, and the specific technique researchers used, precisely measuring the brief dimming of combined starlight as the planet slips behind its star. Each orbit requires an extraordinary level of sensitivity and timing. Precision, especially given that the entire event completes in a matter of hours thanks to the planet's absurdly short orbital period. Ground-based telescopes, and even Webb's predecessor, Hubble Space Telescope, simply didn't have the combination of infrared sensitivity and thermal precision necessary to reliably capture a measurement this subtle on a target this small and this far away. It took Webb's specific combination of a much larger primary mirror, extraordinary infrared sensitivity, and an instrument purpose-built for exactly this kind of precision thermal measurement to finally make a discovery like this possible at all. This finding also matters considerably for how astronomers plan their next steps, both for 2I561b specifically and for the broader population of ultra-short period rocky planets already sitting in exoplanet catalogs, largely unexamined with this exact question in mind. Researchers have already indicated that follow-up observations, potentially including additional Webb time, dedicated specifically to identifying the actual chemical composition of whatever gases surrounding TOI 561b, are a clear priority moving forward. Determining exactly what elements make up this mysterious, apparently self-regenerating atmosphere could help confirm or challenge the wet lava world hypothesis directly, rather than leaving it as the best available explanation among several competing possibilities. And astronomers across the broader field are now openly discussing whether other previously studied ultra-short period planets, ones long assumed to be simple, bare, airless rocks based on older, less precise instruments, might deserve a fresh look using Webb's considerably more sensitive capabilities in case TOI 561b turns out to be not a singular anomaly, but the first confirmed example of a genuinely new category of planet hiding throughout the galaxy. So when you hear that James Webb found something that shouldn't be possible, understand exactly what the claim is actually built on. It's not exaggeration, and it's not a mystery invented purely for a dramatic headline. It's real, carefully measured data. A 900-degree temperature discrepancy on an ancient, punishingly close orbiting rocky world, one that, according to every model astronomers trusted before this measurement, should have been stripped down to bare, airless stone billions of years ago. Instead, TOI 561b appears to be doing something genuinely unprecedented, quietly sustaining, and possibly even continuously rebuilding an atmosphere directly out of its own molten interior, defying assumptions that have anchored planetary science for decades and forcing researchers back to the drawing board to figure out exactly how a world this extreme has managed to keep its sky intact for so impossibly long. If a planet baking under conditions this extreme can still defy the models scientists trusted for decades, imagine what else out there is quietly breaking the rules we haven't thought to test yet. Subscribe now so you never miss the next discovery that shouldn't be possible.